Yeah.
So here we are, and I have a problem up here, and our goal is to take this problem through all the steps to get to the beaker drawing. And I honestly think the beaker drawing is like, once we get through this, we've gotten through a lot of chemistry, and we just have a chapter on thermochem, which I think is super interesting. It's about energy. And we have plenty of time to do it. And then at this point, it's kind of like you're running a marathon. And if you're still in the game with a good stride at this point, you're going to get over the finish line just fine. But it doesn't mean stop working. It just means keep doing the work you're doing. So go ahead and maybe write that down and start to write some formulas. Our starting place will be a balanced chemical equation. So this week I had to, so teachers, full-time faculty have to do other jobs too. Like we get put on committees that we didn't necessarily choose. I'm on a couple of committees. And one of them is a tenure track committee for a language teacher. And so I've been inside a language teacher's shell this week. And the class is also a 5-unit class, like our class is. And I'm just looking at it thinking, wow, chemistry is just a different world. I knew it was true on the ground, but when you get to actually spend some time in someone else's class, you remember and realize science majors are hardworking. A lot of people start out as science majors as a freshman in college, but not as many graduate. And the reason is it just requires more time and commitment than a lot of things do. So good for y'all for being here. Okay, so our goal is to end up with a picture of a beaker. And the picture, and this is one of your assignments this week. I don't know if you've seen it yet. And there is a video on it on the page, but we're going to walk through a problem because it doesn't hurt to go through it a couple times. We're going to end up making a precipitate. And then we're going to have to state what the precipitate is. So if we're starting with iron 3 and chloride, that's one reactant. And potassium carbonate, that's going to be the other reactant. When they switch partners, we're either going to have potassium chloride or iron 3 carbonate. Turns out carbonates are typically insoluble and iron 3 is not an exception. So our solid, our precipitate here is going to be iron 3 carbonate. But there's still going to be things floating around the beaker. There are still electrolytes in solution. So if iron 3 carbonate is what precipitates, there is going to be potassium ions and chloride ions floating free in solution as spectators. And then we're going to have to figure out between the iron 3 and the carbonate, which one ran out first, which is the limiting reactant. Is the limiting reactant carbonate? If it is, then there's a little bit of iron 3 floating around. Or is the limiting reactant iron 3, in which case there's a little bit of carbonate floating around. So we have to decide what the excess reactant is. And in this case, it's going to be one of those two ions, the one that wasn't completely consumed. Okay, so at this point, that's the whole hour. That's what we're going to do. And then if there's any questions on what the goal is, this is a good time to ask. And you are the students that are still here and are being scrappy and are going to finish the class. And so if you have questions or even a clarifying statement that you'd like to make, go ahead and say that thing. Hi, Melissa. Glad you joined us. Okay, so in order to do this problem, we're going to have to start with writing a balanced chemical equation. And the equation we start with is called a molecular equation, even though there will be no molecules present. There's water in the beaker, that's a molecule, but that's not part of the reaction. And then from that, we're going to use our solubility rules to come up with a total ionic equation. And then we'll cancel out spectators to come up with our net ionic equation. And then we're going to make some calculations. So once we know our net ionic equation, which is going to be iron 3 plus carbonate, makes iron 3 carbonate, we can see how much product can be produced. So from this, we're going to get our theoretical yield using stoichiometry. And so one of the questions we're going to answer is how many grams of product? But once the product is produced, we're going to still have some ions floating in solution. There's going to be potassium ions and chlorine ions, and then whatever the excess reactant is. So if the iron 3 is consumed, the SX reactant is carbonate, that, for example. And what the other question will be is, what is the concentration in units of moles per liter of these things? So after we figure out using the theoretical yield, like that's our goal, to find grams of product, we're still going to want to know what the concentration of the other ions is. Oops. Concentrations in capital M means molarity, which is moles per liter. So moles of this ion per liter of solution. Go ahead and write the formulas for iron 3 and chloride and potassium carbonate. Once we've correctly written the formulas, then we can balance the equation by adding coefficients. And then we can use our solubility rules to make a total ionic and cancel out spectators to get a net ionic equation. Okay, so these steps don't have to necessarily be done in this order. Like, part of the problem was to come up with the net ionic, so I did that first. I didn't have to do that first. Another part of the problem is to come up with the moles of each of the ions and the new total volume. And we're going to do that because we want to come up with the molarity of each of these ions that are still floating in solution. And so let me talk about molarity just for a minute. So molarity is a unit of concentration that chemists prefer. It's not the only unit that we use, but it's very common, and it's the one that we use most in general chemistry. And it is moles of something, a solute, so one of the things in the mixture, per liter of solution. And so let's say that I had, for example, 0.12 moles of lithium ion in 125 milliliters. So I'm going to convert that to liters. I would say I have a 0.96 molar lithium ion solution, or the molarity of the lithium ion solution is 0.96 molar. So when we say this capital M, in this context, we would say molar, and people understand that means moles per liter. But the question would be, you know, what is the molarity? And that would also be a capital M. So M stands for molar and molarity. Yeah, so what we need to do now is find out what our new total volume is, and then what the moles of each ion is. So there's 4 problems here: the moles of iron 2 before we mix iron 3 before we mix things, the moles of chloride, the moles of potassium, the moles of carbonate, and then the new total volume, which is 50 plus 75 mils. Questions on molarity? Okay. So for example, I would take, I have 50 mils of means multiply, 0.12 molar, and it was iron 3 chloride. And my goal is to find out how many moles of iron 3 I have, and then in a different problem, how many moles of chloride. So the first thing I want to do is interpret what that capital M means. I'm going to change it from a capital M to what it means, which is moles per liter. So I'm renaming the capital M as MOL of iron 3 chloride per liter of solution. After I rename molarity, I notice that I have a volume in milliliters and I want it to cancel, and milliliters and liters don't cancel. So I'm actually going to rename liters now as 1,000 milliliters. When I do that, my milliliters will cancel, and I now have moles of solute. But the solute is a formula unit. It's a cation plus the anion, and my goal is to find just the cation at this time. So I'm going to look at the formula and notice that there's 1 mole of iron 3 in every mole of iron 3 chloride. It's a 1-to-1 ratio. And so now moles of the solute, iron 3 chloride, have canceled, and I have what I want, which is moles of iron 3. I started with 3 sig figs times 3 sig figs. My answer should have 3 sig figs. To find the molarity, I'm going to say, what is the molarity of iron 3? It's 0.00600 moles of iron 3, and whatever the total volume is.
Professor, would it be wrong if we didn't have the charge of the element as our answer?
If you just had iron and you didn't have the 3 plus showing, it would be wrong.
Okay, thank you.
Yeah. Okay, so that's the general idea about how to find molarities, which is one of the things that we're going to do to answer the question. And then another question that we're answering is how many grams of product? And so that's limiting reactant stoichiometry. I want to talk about that just for a minute. Can I erase the bottom half of this screen?
Yeah, I'm good.
Okay, so let's do this part first because we need to see what runs out and what's left over, and then we can go through and find the molarities of each thing. So I need to know the moles of this. So I'm going to go from molarity times volume equals moles. Moles per liter would be molarity. And if the volume is in liters, molarity times volume equals moles. So I want to find the moles of iron 3, and then I can find the moles of product. And then I can use the molar mass to find the grams of product. I'm going to do that twice, once with the iron 3, and then molarity times volume equals moles of carbonate, and do the same idea. To moles of product to grams of product, and we're going to see which produces less product because we have 2 starting amounts. This is limiting reactant stoichiometry. The way that it's different from the limiting reactant stoichiometry we've done so far is because we're not starting with something pure, a solid in grams. We're starting with a volume and a concentration to get to moles. Again, I'm going to rename molarity as moles of iron 3 chloride per liter of solution. And then I'm going to rename liter as 1,000 milliliters so that my milliliters can cancel. It's kind of messy. Questions? So this is a limiting reactant problem. And I started with one set and went to products, got an answer. And then the other reactant, molarity times volume, and got an answer. I choose the smaller answer. And that tells me that carbonate ran out before iron 3 did. Carbonate is my limiting reactant. We could say the limiting reactant is potassium carbonate, but in solution, they're not together anymore. They float around as ions. And so the ion that is in excess is iron 3. Just cross that number out. So I have the answer to one of my questions. How many grams of product? And I now know my excess reactant, because carbonate is what ran out. My excess reactant is iron 3. Okay, I feel like there might be a question or two on this page. There's a lot on that page. And again, I can't see your faces, so I don't know, who's writing and who's thinking and who's waiting. Is that a question, Melissa?
I don't even know what to, I don't know. No, it makes sense. It's just a lot to keep track of.
It is a lot. And we're
I'm just
halfway
trying
done.
to breathe. I'm just trying to breathe. That's all. I know. I've already got 2 pages. I need to learn how to write smaller.
Yeah. So, and I did say there's an assignment this week that looks like this, and there's a video that walks you through a problem that's just like this. And then later today, I'll edit this and post it. Let's see. Kylie's here. Let me see what it says. Okay. Yeah. Kylie, go ahead and log out, and then I'll let you back in. Okay, so our questions were, our goal is to draw this thing called a beaker drawing. And that's what we have here. We wanted to find out some answers to these questions. And we've got one, which is how much product can be produced. And we've also figured out what the limiting reactant is, so we know which one is going to be in excess. So we need to figure out how much iron 3 is left over. This is one of those subtracting problems where we know how much iron 3 we started with, and then we can find out how much iron 3 we consumed, and the difference is what's left over. And we're going to do it in moles. So I'm going to erase some things on this page. Actually, maybe I'll just add a new page. Okay, so my goal now is to know how many moles of iron 3 I began with. And then I'm going to subtract and see how many moles of iron 3 were needed. And to do that, I start with a limiting reactant. So here's our equation. Iron 3 plus carbonate make iron 3 carbonate. I could figure out how many moles are available by doing that process and stopping here. And then I can find out how many moles are needed. And to do that, I'm going to start with my limiting reactant. Molarity times volume of the thing that runs out completely. And that'll give me moles. And then I'll take those moles to moles needed of iron 3. Which is what we did in other problems. When I said how much of the excess remains, we always went back to the limiting reactant to figure out how much of the other reactant was needed, and then there was a subtraction step. So that process is the same. It maybe just looks different because we're starting with solutions. And then we'll know how many moles of iron 3 are remaining. And then to figure out what the molarity of iron 3 is, we'll take those moles that are remaining and divide by the total volume. So that's our plan right now. Now let's see how much we started with. If it's any comfort, that was the most involved calculation. The reason we needed the subtraction step was because we were looking at a reagent that was consumed, but not consumed entirely. We had to see how much we started with, subtract what the limiting reactant dictates we need, and then see what's left over. And then because this is in solution, and molarity is a question, we had this other step where we took what was left over, divided it by the total volume to come up with the molarity. There's not a lot of iron 3, but there is some in that water. And when is this really important? If it was, for example, lead. If we had lead 2 ion floating in water, even a little bit causes brain damage, so it does matter. So there's not a lot, but there is some. And so we now know for our excess reactant that it was iron 3, and the concentration is 0.00200 molar. There's not a lot of iron 3, but there's a little bit floating around. So the last thing we need to answer to complete this is what is the concentration of potassium and chloride ions? And that's a lot more straightforward because there's no reaction going on. We're just looking at a dilution. So we just need to look at, here's iron 3 chloride. How many moles of iron 3 or how many moles of chloride are present, and divide that by the total volume, and then we'll have the molarity. Here's potassium carbonate. How many moles of potassium are there? Divide by the same total volume, 125 mils, and then we'll have the concentration of potassium, and we can answer our questions. The only, it's not trick, but the only thing that's different from before is for every formula unit of iron 3 chloride, there are 3 chlorides. So every mole of that has 3 moles of chloride. Same idea for the potassium carbonate. We took 2 potassium ions to balance that carbonate charge, so there is a 2-to-1 factor in there. Okay, so that's what we're going to do now is figure out what the molarity of chloride and potassium ions are, and then we'll finish our drawing. Questions? Oops, that was chloride. Alrighty, are there any pages that you would like to see? So I want to indicate in my beaker drawing that there's a lot of potassium ion and chloride ion. And so I'm going to add some more Ks. And remember to keep their charges because they're floating in solution. And some more chlorides. But I only have one iron 3 because I'm indicating the concentration of that is very low, 0.00200 molar. When you do this worksheet, maybe do it on a separate piece of paper, and then before you submit it, make sure that you have all your work laid out so it's clear to see, where I can see you got your answers from, and then make sure that you have a beaker drawing that indicates what the solid is, has a little bit of the excess ion, and then a lot of the spectators, and then make sure that you've made it clear what concentrations and amounts of things are. That's all I got. I do have one announcement. So I will be working next week, but I'll be working from Mexico, so I'm not going to do Zooms. And so Zooms will be canceled next week, but I will still have my computer and I will still respond to emails. And if anybody needs to Zoom privately, I think we're 2 hours apart. We could probably sort that out and still meet. So if there are questions, certainly you could ask questions through email or through Zoom. And then tomorrow is Halloween. And so having a meeting at 5 doesn't make sense. So I'm going to cancel that one too. I will see you in a week.